Now you should understand about basic setting of the like spring motion, right? But like, in the previous slide, we talked about equilibrium solution, equilibrium position case only, right? But now we can make it more, fun, okay? What does it mean? We're gonna apply some extra, like external force, like to the spring, then we can make the dynamics on the spring motion, okay? So we will talk about it like in this slide, okay? Before starting this one, let me try to copy and paste my figure that I gave you in the previous slide here. Okay, here we go. So I had a spring here, but it was a little bit stretched because of the mass of the object, right? So the length of this stretched spring is now L plus capital L, okay? As we talked about it, for this equilibrium position, we had two force, right? The first one is gravitational force, and the other is spring's force, right? So let me write that one on here, okay? So the force, weight force M, let's say W is equal to mg. M is the weight of, like mass of the object, right? And the other was like applying the backward, and let's say it is spring force that is negative because that is opposite direction of the gravitational force, right? And constant K for proportion and the stretched length L, okay? Now I'm gonna apply external force for this like situation, this equilibrium position, then it will be stretched out. And we're gonna say that is displacement. Is that okay? And we will talk about the like, total force for that motion, okay? We're gonna say that is f of x, okay? So basically, like it is based on Newton's law of motion, which is ma, right? Here we go. So Newton's law of motion, which is F equal to ma, and acceleration a is the like second derivative of your displacement of u, okay? So since your a can be written by u double prime, and by plugging back, we can say your final force F is mu double prime, okay? But like for this motion, this dynamics, and there are four separated like force applied in here, okay? So we're gonna talk about that one, okay? Here we go, okay? As I told you, we're gonna like stretch out this one as like this way, okay? Ut is the length, which is position, okay? Or we can say it's displacement, okay? So here, there are four forces, okay? The first one is weight. We talked about this one already, right? Weight, W is equal to mg, which is based on the gravitational acceleration, okay? And the second one is spring force. We notate by Fs, right? And that is backward, and basically it's K times L plus U, because the original length was the L, and stretching by the mass was capital L, and now it's like even more stretching by pull down, right? Which is displacement U. So your spring force is applied like this way. You know why we have L plus U, right? Because U is the displacement, okay? And then also we have to think about damping force, right? Damping force is kind of like, resistance from air or some medium, whatever, okay? So like we have to think about that one. That is also proportional to the velocity, okay? So like we need another constant gamma, and we can say that is um, here. Definitely it is applying opposite direction of your displacement. That's why that is negative sign, okay? You understand what I'm saying, right? And another one is like, external force, right? For this dynamics, I put down that force. We're gonna notate by capital F, okay? And all those like four forces applying to the like final total force total force F, okay? So your total force F of t, F of F of t, that is F of t, okay, is equal to weight W and spring F of S and damping F of D and pull down force, which is F, which is, we say it is external force, okay? And all those things apply to the like displacement motion, okay? So like since your F of T is mu double prime from the Newton's law of motion, and it is equal to weight W, which is mg, and f of s and f of d is applying to the backwards direction. So like we're gonna like, there's negative sign. So it is notate here, okay? And this guy, and external force, which is capital F of t, okay? And like in the previous slide, we talked about equilibrium position, right? Which is mg minus k capital L is equal 0, okay? I state here. And then we can say this two part is equal to 0, okay? Then when you simplify this one, this will be written, okay, let me rewrite here, okay? M u double prime is equal to minus k u minus gamma u prime plus f of t, okay? And when I move everything to the left-hand side except f of t, then you can have m u double prime plus, no, let me write the plus gamma first, okay? Plus gamma u prime plus ku is equal to f of t. Are you with me so far? Look at that. That is second order linear differential equation, non-homogeneous, right? Because there is the external force, okay? And also, all m, gamma, and k's are constant. So you have constant coefficient for your second order linear differential equation, okay? That is exactly what we learn how we can take care of this one, right? And then we can solve it, okay? And to solve this problem, we need initial conditions. So we need u0 and u prime of 0. What does that mean? U0 is the like, the initial displacement, okay, which is like, the length you put down, okay, and u prime 0 is the like initial velocity, okay, when you release the like your spring, and then like, there is the initial velocity maybe, right? And that is the initial condition for this problem, okay?